We're going to start off really basic. All matter is made up of atoms. This is a model of an atom. This is called the Bohr model. I'm starting now, fellas. This is totally wrong, by the way. Electrons aren't little tiny satellites that orbit a central nucleus in rings. But this model explains an awful lot and is pretty good. But Mr. Perugia would right away remind me to tell you this is not how it works in real life. How it works in real life is strange and weird. The best explanation is go dive into the quantum equation, because that's really what predicts everything the best, but it's weird. For now, though, we'll use the Bohr model, and we're going to say that matter is made up of atoms, and the atoms have a central nucleus that contains protons and neutrons. And there are electrons in, now it's become more common to say shells. We used to say orbits, but you can't go electricity is what's pulling me in a circle and call that really correct. When atoms bond together to form solids, all the action happens with the electrons. The electrons can be tightly bound to the atoms, as in covalent solids like glass. These will be insulators. Insulators, and that's a term you'll need to know, are objects that don't allow electrons to move very freely. Your skin is actually a pretty good insulator. But, like any insulator, with enough oomph, you can overcome it. What do I mean by oomph? We'll have to define oomph with electrons and electricity later on scientifically. Electrons, Drake, can also be free to move around, as in metals. We call these conductors. If you want our Bohr model, so in a covalent solid like glass, the electrons are very locked into their shells and locked around specific neutrons, nuclei. In a metal, electrons are free to move from atom to atom to atom to atom. And again, technically that's wrong, but Kayla, it's a good enough model that it'll explain an awful lot. We'll go with it. The subatomic particles, like protons, electrons, and neutrons, have a property. A wondrous property, a property that we have harnessed and that explains an awful lot. We have named this property charge. It's charge that's responsible for both electricity and magnetism. Magnets are also a result of charge. Some basic facts, and you probably remember this from Science 9, especially if you had me back in Science 9. There are two types of charge that we call. What are the two types of charge? You know this. Max. Positive. You know what? That's too much writing. My abbreviation for the word positive, I don't just write a plus sign, because whenever I see a plus sign, I think I'm missing an equation. I go hunting for an equation. So this is my own thing. If I want to abbreviate the word positive, I put a plus and a VE next to it. Positive. And my abbreviation for negative is a negative and a VE. If I just write a minus sign, I go hunting for the rest of the equation. That's me as a math nerd, Tori. You won't see that on any textbook. That's just something that I came up with. What are the units for charge? This one's a bit more obscure. Give you a hint. Begins with the letter C. I heard it. Yep. Charge is measured in coulombs, symbol capital C. 1 coulomb of charge is massive. 1 coulomb of charge, if you absorbed it all at once, would not just kill you, your skin would char, your hair would burst into flame. It's massive. So almost all the time, we'll be dealing with micro coulombs. We'll talk about that, but you're going to see time and time again, we're going to be using that. It's on our formula sheet, and you're going to end up memorizing what micro means because you get sick of looking it up. It's a 10 to the negative 6. Little note about positive and negative. Positive and negative were named by Ben Franklin, the same Ben Franklin on the bills and that you've heard of in American history. He got them wrong. He really should have called electrons positive, and he should have called protons negative. Had he done that, a lot of the math would make much more sense, because the whole losing an electron and becoming positive because it's a minus, you wouldn't have needed to worry about that. You would have said, I've lost a positive, I'm one down, because all the action is happening with the electrons. He didn't know that. Very little of the action happens with the protons. Oh, charge is represented by the letter, well, units C, but charge has a symbol. What letter did we use for mass in kilograms? What symbol did we use? Come on, obvious, huh? M. What letter did we use for force in newtons? What letter do we use for charge? Q. We can't use the letter C because the letter C already is used for the speed of light. It's taken, it's special. Why Q? Well, another important fact about charge is that it is quantized. That's where the word quantum physics comes from, and it's why the letter Q is used. What that really means is charge comes in chunks, and there is a smallest chunk. What's the smallest unit of money that we used to have that we phased out of existence a few years ago? But what's the smallest amount of money? Pennies. And all of our monetary amounts are built up on different multiples of pennies. A quarter is 25 pennies. A dime is 10 pennies. Well, it turns out there is a smallest fundamental charge as well. So with money, the smallest unit is the cent, and any larger amount, a quarter, is 25 cents. A dollar is 100 cents. With respect to charge, the smallest unit of charge is called the elementary or fundamental charge, often symbolized with a lowercase e. A lowercase e doesn't stand for electron. It stands for elementary charge. But it is the charge of a proton and an electron. What is that charge? You know what? It's on your formula sheet. Go look at the data. Find for me the value of the elementary charge. It's going to be right above where all the masses of the planets and stuff were. Yeah, we already got that a little while ago. That was good concentration. Okay. The elementary charge, the charge on an electron is 0.00000000000000000000000016 coulombs. Oh, sorry, negative 0.000016. Charge on a proton, positive 0.00016, 1.6 times 10 to the negative 19 coulombs. Okay? All larger charges are multiples of E. If you want to find out how many electrons you're moving around, the total charge is the number of electrons times the elementary charge. I got to go nerd on you here, a little technical. Those of you that are really nerdy, you may be aware that this is already way out of date. This was okay in about 1920. And then we learned that there are even smaller subatomic particles. We learned that protons and neutrons are made up of quarks, and quarks have charges of 2/3 E and negative 2/3 E and 1/3 E and negative 1/3 E. And so I'm lying to you, but I've been lying to you almost all year long. We've been ignoring air resistance. We've had our Atwood machine, our pulleys have had no friction, and our ropes have had no mass. So, hey, one more lie to add to the stack. We're not going to worry about quarks. In this course, you're going to get a data page. You've seen it already. And it's going to list the masses of the subatomic particles, electron mass, proton mass, and neutron mass. Why do you need the mass? Because if we're doing a force, F equals ma. And it'll give you the fundamental charge. The data page does not explicitly list the charges, so you'll need to remember the following. The symbol for an electron is E minus. What that means, it has a charge of negative 1.6 times 10 to the negative 19 coulombs. The symbol for a proton is a lowercase p with a plus. That's to say that it's got a charge of positive 1.6 times 10 to the negative 19 coulombs. The symbol for a neutron, N0, what's the charge on a neutron? As a number. A neutron walked into a bar and said to the bartender, "How much for a drink?" The bartender looked at the neutron and said, "For you, no charge." Right? An atom walked into a bar and said, "I've lost an electron." The bartender said, "Are you sure?" The atom said, "Yes, I'm positive." The bartender says, oh, then I'll keep my eye on you. Okay, there's a whole series of jokes we can go into. Yes? Like right there? Okay, don't overcomplicate that. By the way, look up, everybody. Don't write this down, look up. If you have $1.19, how many pennies do you have? 119. Or if you have 119 pennies, you go 119 times 1, and that tells you it's $1.19. If you have 3 million electrons and you want to know how much charge you have, it's going to be 3 million, sadly not times 1, times 1.6 times 10 to the negative 19. That'll tell you how big the charge is that you have. Don't overcomplicate it. And in fact, we're almost never going to use this. We're going to move beyond it. Although this does not need to be memorized, you might already know from Science 10 that an alpha particle, symbol, is a helium nucleus containing 2 protons, 2 neutrons, and no electrons. What's the charge? Well, charge is the number of charged objects times the elementary charge. How many charged objects does an alpha particle have? I gave you a list here. 2. Positive or negative? Okay, if it had 2 electrons instead of 2 protons, I just put a minus sign in here. Times, what's the penny equivalent of charge? 1.6 times 10 to the negative 19. Don't you dare pull out your calculators. 1.6 times 2, it's 3.2 times 10 to the negative 19 coulombs. That's the charge on 1 alpha particle. By the way, that's why, Nick, I said to you, because 10 to the negative 19 is so small, that's why I said 1 coulomb of charge, you're absorbing a massive number of electrons. That'll fry you. That'll fry you. Sorry, if you absorb it all at once. I got to say, there's a time factor too. If you spread it out, it's not too bad. So, for a conductor, electrons flow freely and easily. For an insulator, electrons cannot flow. However, you can shift their orbits slightly, and we call this polarization. You can make one side of the object slightly more negative and the other side of the object slightly more positive, even though overall you still have a neutral charge. You can move them around a little bit. This is one of the 4 fundamental forces, electromagnetic force. Charges exert a force on each other. By the way, don't write this down. Suppose we had a box sitting on a counter. What are the forces on it? Get the obvious one. Gravity is a fundamental force. What else? Is it sinking to the ground like quicksand? Is it flying like... So what have I told you to write there? Normal force is not a real force. Okay? We use it. It's a good model. If you take your hand and you try and push through the desk, try it right now. Push your hand. Try it. Why can't you push through the desk? Because your hand is mostly empty space. Atoms are mostly empty space. The desk is mostly empty space. Why can't you go right through? Do it again. Seriously. Are you touching the desk? No, you're not. You've never touched anything in your life. You never have. What you're doing, Connor, the electrons on the surface of your skin are getting very, very close to the electrons on the surface of the top row of atoms, and the electrons are repelling each other. That's the force that you're feeling. We've called that the normal force at the higher level because I don't want to dive into the 4 fundamental forces every single time, but for what it's worth, technically that's what the normal force is. It's the repulsive force of electrons pushing on electrons. And this brings us to our segue. Key idea. This you'll have to memorize. It's not on your formula sheet, but I think most of you already know this. Like charges will blank, unlike charges will blank. I'm looking for 2 words. The 2 words are repel and attract. Like charges will repel. Unlike charges will attract. And because, Robbie, the electrons in your hand are on the outer surface, and the electrons of the top row of molecules of the desk are on the outer surface, you have electrons repelling electrons. That's what you're feeling. You've never touched anything in your life. all you've ever felt is the repulsive force. And your skin and your brain is so used to that, you translate that into touch and contact and pressure, but you never have. There's always a microscopic gap. This is also where we get the saying, opposites attract. It's really, unlike charges will attract each other. They'll exert a force towards each other. Like charges will repel each other. So if we were drawing the direction of the electric forces here, we would have a force that way and a force that way, repelling, because they're like charges. Here, we would have a force this way and a force this way, attracting, because they are unlike charges. And that's going to be important. We are going to have to be very careful now, again, with direction. Drake, like, repel, unlike, attract. That's going to be your cue for the next month or so. Like, repel, unlike, attract. Like, unlike, you're going to be my guinea pig, that's going to be my cue. One of the safest places to be during a lightning storm is inside a metal car. Why? The lightning just jumped a kilometer from the sky. I assure you, it can jump this much further and get to the ground. The rubber tires have nothing to do with it, but people always say that. That's a great, badly thought through. Here's what I mean. It's an immediate, obvious hypothesis, but when I phrase my response, I saw you start nodding and going, oh yeah, I should have thought of that. It's just jumped a kilometer from the cloud. What is an extra 30 centimeters going to mean? Nothing. Why is a car so safe? Drake, are you ready? Like, unlike, good. Connor.
All the electrons go around you.
It absorbs so many, first of all, cars made of metal, which is conductive. It absorbs all these electrons. What do these electrons want to do? Like, the only way they can repel each other is to gather on the very outside surface that's as far away as they can get from each other. Where are you? Inside. We call this phenomenon a Faraday Cage, named after one of my nerd heroes that I'll go on rants about, Michael Faraday. He was the one, most of our electricity and knowledge was discovered by him. He invented the electric generator and the electric motor. That alone would get him a place in the Science Hall of Fame, but he did much more. He proposed that if someone was wearing a suit of metal, that any electricity that they absorbed would gather on the outside of the suit of metal, and that the person would be fine. We call that a Faraday cage. Put your pencils down, look up. Why? Fill in the word, Drake.
Repel.
If you want to sound really science-y, the car acts like a Faraday cage. We'll be talking about Faraday cages because they're pretty cool. I'll show you some other examples of wearable Faraday cages. Okay. All right, here's another thought experiment. Yeah?
Would it be safe to touch the car after the lightning strike?
Yeah.
Okay.
It's great.
What happens to the electricity?
I think it also jumped down to the ground as well. I don't think we saw the arc. It might have been hidden, but yeah. Yeah, because the only way you can get electricity to move, there has to be a completed circuit. So there would have been a continuous circuit to the ground. A negative rod is brought close to an insulating ball. The ball is first attracted and then repelled by the rod. Sounds like half of teenage relationships. What? First attracted, then repelled, right? No? Come on, you've seen all your... Anyways. Explain why this happens. Let me first of all show you that it does happen. Put your pencils down, look up. To explain what happens, a charge diagram is going to be very helpful. However, in real life, there is gajillions of charge. And that's my way of saying it's more than trillions, it's more than quintillions, it's probably more than septillions. It's many, many charges moving around. I'm only going to draw 3 or 4. It's a charge diagram, we just want to get the gist. Let me zoom into this first diagram. In this first diagram, the ball is neutral. So the way I'm going to show that is I'm going to put 2 plus signs and 2 minus signs on it. It's neutral. Really, a gajillion positives and a gajillion negatives. Now the rod is negative. It's got a couple of pluses, but overall, it's got more negatives than positives. When something is charged negative, it doesn't mean there's no positives. It just means there is extra negatives compared to the positives. Okay. Drake, like, unlike. As we get close, this negative rod here is going to move all of the positives to that side and all of the negatives to that side, because like, unlike. So the unlike positives are attracted. Now, this ball is not a conductor, it's an insulator. We have polarized the ball. We have moved some charges around. But now some of these negatives are going to jump across and get onto the positives. So we're going to have this. Still mostly negative here. Still two positives, but now we're going to have extra negatives have jumped across. So now that pith ball, that little round ball, is no longer neutral. How is it charged overall? How is the rod still charged? Are they charged like or unlike? Drake, like charges will? Like charges will? Like charges will? Thank you. And so we end up with negatives here, those original positives there, the original negatives, that was neutral, but it gains some extra negatives. That's what's going on. That's why you see at the end, it's trying to get as far away as it can from that negatively charged rod. We call this charging by conduction because we made contact. We had to touch it. Conduction requires contact. You can also charge something, so you can make a little note here. This is charging by conduction. We made contact. We had to touch it. You can also charge objects by induction. You can induce a charge. You can create charged objects without touching them. I don't have this one set up. So it says this: two uncharged metal spheres are fixed onto supports and are touching. And right now, they're neutral. There's my charge diagram. Again, Robbie, please remember it's really a gajillion charges, not 2 and 2, but this is our diagram. A charged negative rod is brought in close to the spheres. With the rod still in place, the spheres are then separated. The rod is then removed. Show by drawing how the charges are distributed in each diagram below. Let's zoom in again. Okay. What's the charge on the rod? Negative. Let's draw that in. A couple of positives, but it's overall negative. Okay. Drake, like charges. So what's going to happen is all of the negatives, of which there were 4, are going to get as far away as they can. They're going to move to the right-hand sphere. And all of the positives, because unlike charges attract, they're going to move to the left-hand sphere. Both spheres overall are still neutral. It's still 2 and 2, 2 and 2. Then, if we just physically pull this sphere sideways and separate them, we'll end up with that, and this is still negatively charged, as a permanent state. And if I now remove the rod, I have managed to charge both spheres without actually touching the spheres with that rod. I didn't actually transfer, I didn't conduct any charge, I induced a charge. I now have one sphere charged negatively and one sphere charged positively. A more complicated version of this is going on if any of you have an electric toothbrush, because we don't want metal contacts around all that water. All electric toothbrushes use an induction charger. And that's probably going to be, in about 2 years, the standard for all smartphones, where you're going to lay your smartphone down on a pad rather than plug it in, and it's going to use an induction charger. Some of you may have that already. It's a more complicated version of this, but it's the idea of I don't have to touch something in order to send charge. So if you have two fixed electric charges, the force between them is given by Coulombs Law. Coulomb found that, like gravity, electricity is also an inverse square law. He found this. The electric force, I'll put a little E there for electric, is equal to, and then put your pencils down and look up. Let me show you how he put it together first. He said it depends on the magnitude of the charges multiplied together. Don't write this down yet. Divided by the square of the distance between them. However, this would give you an answer in coulombs squared per meters squared. This wouldn't give you an answer in newtons. So just like for gravity, where we put a big G there, which was the conversion factor, we're going to put a lowercase k there. This is Coulomb's law. It's on your formula sheet now. Write it down. It's the first equation in the electrostatics section of your formula sheet, where much of this is familiar. Hey, James, what does letter F stand for? What has F stood for since Physics 11? Force in units, newtons. Now, this is the electric force, but it's a force. So also, there's going to be some way that we can also write that as MA. We'll get clever and do that later. K, G was 6.67 times 10 to the negative 11. That's what we needed to put there as our conversion factor. K is a much nicer one. It's 9 times 10 to the 9th. In fact, most of you will memorize that one and get sick of looking it up because it's a 9 and a 9. It has weird units. What would the units for K be? Newtons meters squared per Coulomb squared, I guess. Newtons meters squared per Coulomb squared. That cancels out the Coulomb squared, cancels out the meter squared, and gives you an answer in newtons. 9 times 10 to the what? 9. Remember, gravity was 6.67 times 10 to the negative 11. That means electricity is stronger than gravity by a factor of 10 to the 20th. It's way stronger than gravity. Gravity is weaker than weak. You think it's the biggest fundamental force. It's by far the weakest fundamental force. Q1 is the charge of the first object in coulombs. Q2 is the charge of the second object in coulombs. And then again, D or R, I always use R. It's the distance between the charges in meters. It's a scalar equation. We will figure out the direction ourselves. Do you know how we're going to figure out the direction ourselves? Like, hello? Like, unlike. So we're going to try this again. It's a scalar equation. We will figure out the direction ourselves. Do you know how we're going to figure out the direction ourselves? We're going to use like, unlike. I need you with me here. Unlike, attract. To find the direction of the force, we use, Drake, help us fill this in. Like charges, unlike charges. Put your pencils down, look up. Example 2 says, find the direction of the electrical forces on the positive Q charge. We want to find the direction of the electrical forces, Robbie, on that one there. How many charges are there in this little system grand total? Count. No, I mean, sorry, how many objects are there? Like, how many charged objects are there? There's no way to do 4. If you can figure out a way to do 4 all at once, there's probably a Nobel Prize for you. In fact, there's no way to do 3. This is the famous 3-body problem. We can only do 2 at a time. So which one do we want to find the force on? This guy. We're going to find the direction of the force. You know what? Let's label these. Let's call this charge A, charge B, charge C, and charge D. We're going to find the direction of the force on charge A from charge C. We're going to find the direction of the force on charge A from charge B. We're going to find the direction of the force on charge A from charge D. And then I think we're going to add them tip to tail and get a net resultant. So let's start with the easier ones. Charge A, positive or negative? How big? Q. Charge C, positive or negative? Do you say negative? Unlike. Drake, unlike charges. So charge A is going to feel a force that way from charge C. You okay with that? What about charge B? What's the charge on charge B? Negative or positive? Negative? Positive? Unlike charges, Drake, unlike? So charge A is going to feel a force that way. Now it is true forces come in pairs, so B would feel a force towards charge A as well. I don't care about that. I'm only drawing the forces on charge A. What about charge D? Like or unlike? Like charges what? So it's going to push it away probably in that direction. I think it's going to be smaller because it's further away. All three charges, B, C, and D, have a charge of 2. Just 2 are negative and 2 are positive, but they have the same magnitude charge. If I wanted to add these together, I would get something like this. That plus that plus that. If you wanted the direction of the net force, I think that. Ish. I think initially this would move in that direction. Now, as soon as it starts to move, your distances are changing, your forces are changing, the situation is changing. So you can't say, oh, it's just going to move and end up right there. No. In fact, the closer it gets to that guy, the more it's going to be repelled by that charge. So, to solve force problems, how many more am I doing here? Ooh, a bunch more. We'll see if we get through it all today. To solve force problems, first thing, you need to express the charges in coulombs. Then we're going to substitute the charges and the distance into Coulombs Law to find the force. And then to get the direction, we're going to use like, unlike. Yeah. Little technical comment. If we have unlike charges, one's positive and one's negative, technically the answer you're going to get is negative. We don't want a negative answer. The negative is to indicate attraction. We should not conclude that the force is negative backwards, or whatever negative means. We should drop the negative in our answer. Quick look at money. So, just before you go, hang on, Sinead, 1 second. Basically, the negative is not needed, and some people write Coulombs Law using absolute values. For some reason, this got kind of smooshed up. I'd like you, on your formula sheet, on your yellow sheet, where it says F equals K Q1 Q2 over R squared, with your pen or pencil, put a little absolute value sign in there to say to you, do not put negatives and positives in. I'm letting you guys do that for the first time this year. Normally I made kids memorize that, but this year I'm letting you do that. Okay? Now you may, Sinead, go ahead. So, here's an electron in a helium plus atom. What's the force that that electron is feeling from the positively charged nucleus? It's an electric force, so it's going to be K Q1 Q2 over R squared. Mr. Dueck? Yeah, Robbie? This looks an awful lot like this equation. Yeah, it does, doesn't it? Except, Mr. Dueck, gravity always attracts. It never repels. That's true. Is there such a thing as like negative mass or antimatter that would be like anti-gravity? We're looking for it. What's K? Much nicer than 6.67 times 10 to... Also way easier to type on your calculator. Q1 is going to be the nucleus. What's the charge of the nucleus? It's 2 protons. Except what's the charge on a proton? The elementary charge. So the nucleus is going to be 2. What's the elementary charge on a proton or an electron? That's from the sheet. The elementary charge. The second charge is that electron right there. What's the charge on an electron? Well, it's technically negative, but I've told you we're not going to put the negatives into our force equation. Oh, the electron is also the elementary charge. 1.6 times 10 to the negative 19. What's the radius? 2 times 10 to the negative 11. I got that right from the question. Squared. How many newtons of force is the electrical force here? Do you get 1.152 times 10 to negative 6 newtons? I'll go 1.15. I'll go to 3 sig figs. And it's a force, so it'll still be in newtons. James, you might be looking at that and saying, meh, big deal. That's 0.0000115 newtons. That's massive. It's huge. Although the force seems very small, remember we're dealing with electrons which have a very small mass. If you actually want to find the acceleration, because F equals ma, if you take that force and you divide it by the mass of the electron, you get the acceleration is 1.26 times 10 to the 24th meters per second squared. It's massive. It's massive. Gravity is a very weak force. Electromagnetic force is a much stronger force. So in atomic terms, the force that we found is a huge force. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Example 4 says, find the net electric force, magnitude, and direction on the 1 Coulomb charge. Oh, we need to introduce a little term for you. Coulombs are way too big. So you're going to see a great deal of the time, I'm going to give you charges in microcoulombs, once in a while in millicoulombs. Micro from your formula sheet is 10 to the negative what? All you need to do is replace the micro with times 10 to the negative 6 on your scientific notation button. Let's call this charge A, charge B, and charge C. Which charge do they want me to find the force on? Charge B. Here's how I'm going to do it. How many charges are there in this question, grand total? 3. There's no way to do 3 at once. Instead, we're going to do 2 at a time. I'm going to find the force between charge B and charge A, magnitude and direction. I'm going to find the force between charge B and charge C, magnitude and direction. And I'm going to add them vectorially. Now, are we in a nice straight line or are we at yucky angles? Then vectorially is just going to be winner minus loser. If they were at angles, tip to tail. It's going to be K, QA, QB over R between A and B squared. K, 9 times 10 to the 9th. Charge A, 1 microcoulomb, 1 times 10 to the negative 6. Charge B, 1 microcoulomb. Mr. Dewick, wasn't charge A negative? We're absolute value. We don't care about negatives. We're going to use the negatives and the positives to figure out the direction. Divided by, How far apart are charge A and charge B in meters, please? 0.2 squared. 9 times 10 to the 9, times, geez, Duick, times 10 to the 9th. 1 times 10 to the negative 6. 1 times 10 to the negative 6 divided by 0.2 squared. You get 0.225? 0.225 newtons. Direction. So which charge do we want to find the force on? Ignore charge C. Pretend it's not there. Don't do what I'm doing, but pretend it's not there. Is B being pulled to the left or repelled to the right? Drake, these are unlike charges. What can you tell me about unlike charges? So that means B is getting pulled that way by charge A, which is to the left. We're going to repeat this procedure between B and C. If it's okay, I'm not going to rewrite the equation, Julie. I'm going to go straight to plugging in numbers. It's going to be 9 times 10 to the 9th. Charge B, 1 microcoulomb. Charge C, 2 microcoulombs. Divided by, how far apart are charge B and charge C in meters? 0.1? Now, if you have a calculator that lets you backspace and edit, you may find that you can just go change that to a 2, change that to a 1, 0. You get 0.18? Or am I wrong? I forgot the squared.
Yeah.
Get 1.8? Direction. Which way is charge B experiencing a force because of charge C? Charge C is negative, charge B is positive, so is charge B being pulled to the right or pushed to the left? Unlike charges attract, it's getting pulled to the right. How would I add 1.8 newtons right plus 0.225 newtons left? This is going to be winner minus loser. What if they were in the same direction? Winner plus winner. So the net force, 1.58. Direction, what was the winning direction?